Look into the final remarks of coherent and non-coherent detection. We saw that at higher SNR, probability of error is approximately equal to some function of 1 over SNR at some constant for the relay fitting channel. We derived exact probability of error for binary orthogonal signaling and binary antipodal signaling for the non-coherent and coherent cases respectively. And we saw that the performance is much poorer than the performance in AWN channel. For example, for the non-coherent case, we have almost a difference of like 10 dB compared to AWGN. For the AWGN channel case, the probability of error decays exponentially with SNR, where exponent power is SNR, but for the other cases, it's only proportional to 1 over SNR. Now, the big point here is why the performance is poor compared to SNR, compared to the AWGN case. So we need to find out the main and dominant error event at higher SNR. For a given h, the probability of error is given by q function of 2h square SNR square root. Even if the average SNR is high, this h square into SNR can still be very small if the value of h square is close to 0, because as we saw before that h has a variance of sigma square or 1 if it is normalized and mean of 0. So h can have a very less value, and again if we take the square of this h, this could be very close to 0. And even if SNR is high, the multiplication of h square with SNR would be a very low value. This event is called the event of deep fade. So mathematically, the probability of deep fade is expressed as the probability that h square SNR is quite smaller than 1. And this is given in terms of integrals as exponential e to the power minus x if you integrate it from 0 to 1 over SNR, because h square is smaller than 1 over SNR. That is the event, or h square SNR is smaller than 1, and that is exponential. The PDF of this is exponential because the PDF of h square is exponential if h is relay fading. So if you find the integral, it would be approximately equal to 1 minus e to the power minus 1 over SNR, which is approximately equal to 1 over SNR at higher SNR. So even at higher average SNR, probability of deep fade is significant and becomes dominant. For AWGN case, we don't have this 1 over SNR as the dominant factor, but only the dominant factor is noise being large. So now we go further. How can we increase our data rate or the spectral efficiency? So for that, we need to go and find out the performance of QPSK. So in BPSK, we use real symbols. However, we can use complex symbols without increasing the bandwidth. 2 degrees of freedom. 2 degrees of freedom. However, we can use complex symbols without increasing bandwidth. 2 degrees of freedom are available. PPSK uses only 1. QPSK can use both and still achieve same performance. That PPSK uses the real signal and the imaginary signal. So PPSK is given by plus minus a. So where SNR of BPSK is given by a square over n naught. For QPSK we have 2 plus minus a's. So SNR of Q would be equal to 2a square over n naught. Same energy per bit. That is the same energy per bit. A and A are same for BPSK and QPSK. So the bit error probability in BPSK is given by Q into 2 SNR of B in AWGN case, and Q into 2h square SNR B for fading given h case in terms of relay fading channel. Bit error probability in QPSK is the same as in BPSK. So SNR is however twice. SNR Q is equal to 2 SNR B. So if we put these values, the average BER would be approximately equal to 1 over 2 SNRQ. So if we replace SNR in BPSK result by SNRQ over 2, we get this thing. Now, the good schemes, they use all the available degrees of freedom. If we want to use only real symbols, 1 degree of freedom, we would have to use 4 PAM to send the same rate. So it means that if you are using 1 degree of freedom like in BPSK, so to compare it with QPSK, you need 4 PAM. The problem with 4 PAM that BER would be worse because it is more efficient to pack for a given redeem in higher dimensional space than in a lower dimensional space. That's all for this lecture.